Okay, Michael. So let me sort of jump in on that last thing that you asked me. We've just been talking about how to compute probabilities of optimal actions based upon what human beings are giving us, and that's fine. But it turns out we actually have multiple sources of information, and we would like to be able to combine them. In particular, we have some policy that we've learned that gives us a probability distribution over actions that we learned from the human. That's why it says pi sub h here. And you notice here I'm treating a policy as a probability distribution over actions. And that's all kind of neat. And these, in fact, are the numbers that we came up with in our last quiz. But while the agent is running around in the world, the agent has information from running around in the world, right? There are rewards. I've actually gone through and played Pac-Man, and I've been eaten, and I've won, and I've gone through rooms, and I've done all these kinds of things. And it seems kind of silly to ignore what I actually know about what's going on in the world, particularly in the case where a human being might, in fact, be incorrect sometimes, or may really believe that the optimal policy is one thing, but in fact, for the underlying MDP, the optimal policy is something else. So I just want to ask you a couple of really simple questions. Let's imagine that I've got some algorithm that runs around in the world on its own and learns distributions over actions in every given state, okay? And it says after a little while that the probability that action X is optimal is a third, action Y is optimal is a third, and action Z is being optimal is also a third. And so now I've got two sources of information. I have what the humans told me, and I know that it's 2/3, 1/6, 1/6 because math, and I've learned from experience so far that all actions are equally likely.
Which is pretty non-committal.
It is pretty non-committal. In fact, it might be what happens when you start off. If you had to choose an action in this case, which action would you choose?
X.
Why?
Oh, is that the quiz?
No, that's a question.
Oh, it's Y? Oh, wow. I had no idea why it would be Y.
Explain to me why you chose X. Sorry.
Oh, I see. Why I chose X? Because, well, according to the algorithm, it doesn't really care, doesn't have any reason to believe one over the other. But the human has reason to believe it. I guess there's one missing parameter, maybe, which is how much we should believe the human. And so if we believe the human not at all, it's still not bad to go for X.
But here's the thing. We actually have that parameter because
that was C.
That was C. And in fact, it doesn't matter what C is because that's all inside this distribution. This distribution, 2/3, 1/6, 1/6, actually already incorporates all the information about the uncertainty of the human.
I don't think it does.
Yeah, absolutely does. The probability that X is optimal is, in fact, a function of the data that the human has given us and how likely they are to be correct in the data that they've given us.
But it seems like it could change over time as we've come to believe the algorithm more. Then we should believe the human less.
You know, it's really interesting you say that because all the other the various techniques that have been out there in the world actually do that. They actually try to capture what the human has said and what you've learned in the world, and then over time believe the human less and less often because whatever the real world is telling you has got to be correct. What's actually beautiful about this particular mechanism that we described in the last couple of slides is that parameter C, that confidence that we have, that probability that the human is correct, actually sort of captures everything we need to know. If we are completely certain about the human, then these numbers will reflect that by peaking over whatever action should be optimal. And if we're uncertain about the human, then these things will tend to stay towards the uniform.